Hello everyone, I'm Xiaoqing Yi, an application engineer from NOVOSENSE. Today, I'll make a presentation about NSOPA240x power operational amplifier for resolver driver. It can help simplify the circuit design and improve the system robustness. There are three parts of my presentation: description of resolver system and its drive circuit requirements, NSOPA240x operational amplifier overview and its typical parameters. First, let's take a look at what a resolver is. A resolver is an electromagnetic sensor used to measure the angular displacement and angular velocity of a rotating unit. It comprises a stator and a rotor. The stator winding functions are the primary side and receives excitation voltage, and the rotor winding acts as the secondary side and gets induced voltage through electromagnetic coupling. Typically, the secondary side uses two winding coils that are 90 degrees from each other. When sine wave is used to excite the primary side, a corresponding inductive signal is generated on the secondary side, and the signal size is a function of the rotor's position relative to the stator. Since the mechanical positions of secondary windings has a difference of 90 degrees, the two sinusoidal output signals are also at a 90-degree position to each other. When the primary coil is at different angular displacements or is rotating, the output voltage of the two secondary sides will change accordingly. Therefore, based on the two sets of output signals, the angle and angular velocity of the rotor can be calculated. The right table lists the typical electrical parameters of resolver drivers. Input voltage is the excitation voltage applied to the primary side. Generally, in order to get an inductive signal of sufficient amplitude, the corresponding excitation signal amplitude is often large, typically 3 to 7 VRMs. When sine wave is used for excitation, the frequency will range from tens of hertz to tens of kilohertz. I will use an example to further illustrate the resolver driver requirements. As a resolver is essentially a transformer, its independence can generally be abstracted as DC resistance and inductive impedance connected in series. When the excitation signal frequency is typically 10 kHz, its overall impedance will be hundreds of ohms. As a result, the excitation current on the primary side is relatively large, and the peak-to-peak value can reach plus minus 100 mA, 200 mA, or even higher. Therefore, considerable current output capacity is required to achieve normal drive. A typical drive circuit is shown in the right figure. Generally, a push-pull output mode is adopted to get the maximum output signal. Meanwhile, to achieve higher accuracy and linearity, high slew rate is also required in this application. As can be seen from the figure at the lower right, at 10 kHz and 7 VRMs, the minimum slew rate required is 0.3 V per microsecond. In the conventional solution, discrete transistors are used to build a Class AB output, indicating complex BOM and low reliability. Moreover, neither the cost nor the performance is satisfactory. To address the pain points of the resolver driver, NOVOSENSE has developed the automotive NSOPA240x. Firstly, it meets the AEC-Q100 Grade 1 requirements and supports up to 36 volts power supply and 400 mA continuous current output. It can meet the requirements of various resolver drivers and maintain excellent output swing in case of large current output, minimizing its own power dissipation. The 7.5 MHz gain bandwidth product and 5.5 V per microsecond slew rate can ensure no distortion when driving large amplitude AC signals. Furthermore, this operational amplifier has a built-in RF EMI filter, allowing it to work better in complex noise environments like inverter. In addition, it integrates over-temperature shutdown and current-limiting protection functions, greatly reducing the system BOM for engineers and improving the system reliability. It also supports dual-channel and single-channel modes. Two packages are available: NSOPA240 with thermal pad and TO252, which strike a good balance between small footprints and low thermal resistance. NSOPA240x provides an overcurrent alarm function. When an overload or short circuit occurs, the output current can be clamped. It is designed with two special pins, as shown in the red box on the left figure. They can be used to distinguish between upper transistor overcurrent and lower transistor overcurrent, corresponding to applications of short circuit to ground and short circuit to supply voltage respectively. When the output current returns to the normal value, the indicator pin will be released synchronously. In short circuit tests similar to those specified in ISO 16750, NSOPA240x can help the system meet the requirements easily. NSOPA240x provides an overtemperature shutdown function. When the chip's junction temperature exceeds the shutdown threshold of 173 degrees centigrade, the chip will be in the overtemperature shutdown state when the operational amplifier stops working and the output changes to high impedance state and current output stops. In addition, the chip has a special indicator pin pulled down to zero level, indicating that an overtemperature event occurs. The overtemperature shutdown function involves temperature hysteresis. When the junction temperature drops to 155 degrees centigrade, the operational amplifier enters the normal working state again, and the overtemperature shutdown indicator pin is released synchronously. The right figure gives an example of a typical application. When an overload or short circuit occurs, the chip's power dissipation is higher than the design value, causing a rapid rise in the junction temperature. When the junction temperature is more than 175 degrees centigrade, the chip will shut down. After the temperature cools down, the chip will resume working. This cycle will repeat constantly, that is, the hiccup mode. It can effectively protect the chip from overheating and damages in case of abnormal operating conditions. In the last part, I will describe the key parameters of this operational amplifier. For linear drivers with heavy loads, drive capacity is the main measure. The middle two figures shows the relationship between the output voltage swing of NSOPA240x and the output current. It can be seen that the higher the output current is, the lower the output voltage swing will be. Ambient temperature is also a key influencing factor, and it can be seen that the higher the temperature, the smaller the swing. Even under the harshest conditions, for example, at an ambient temperature of 125 degrees centigrade and an output current of 200 mA, there is only a 0.5 volts voltage drop. This means that as long as the power supply voltage is 0.5 volts higher than the voltage swing, the chip can function normally. One benefit is that the chip's power dissipation can be significantly reduced, thus trimming the system heat dissipation requirements. Another key parameter of the resolver drive is AC bandwidth. In the figure at the top right corner, across the full temperature range, the operational amplifier drives a 100 ohmega load. When the gain is -10, the closed-loop bandwidth is higher than 100 kHz, far exceeding the common resolver excitation signal by more than a factor of 10. The large signal bandwidth at the lower right corner also indicates that the operational amplifier's large signal bandwidth is higher than 100 kHz. To summarize, NSOPA240x is designed for resolver driver applications. It helps enhance current output capacity and large signal bandwidth, and provides robust overtemperature and overcurrent protection functions, thereby improving integration and system robustness. Now samples and evaluation boards are available. You can contact us for further information.